go towards exercise 1.2. What does it say? It simply says that state whether the following statements are true or false. Every irrational number is a real number. So is it true? Every irrational number is a real number, because irrational number are something like 1.414 and something. Okay. And
ma'am, can you explain what is real number?
Real number means like if you draw a number line, then all these numbers are known as a real number, right?
Ma'am.
Okay.
Yes, ma'am.
Because what happened, real number means all the numbers we can show on a number line. Real number means all the numbers. So real numbers which are shown on the number line, they will have the rational numbers and they will have the irrational numbers. So real number is a sum of rational number and irrational number. Clear?
Yes.
Clear? Like if you draw a number line, here you have 0, here you have 1, and here you have 2. Okay. So here you will have like 1.1, 1.2, 1.3, 1.5, and so on. So all these are rational number. All these are rational number. But you will also have 1.141 something endlessly. They will also be somewhere here. Okay. And these are irrational. So whenever we say real number, we count all the numbers on the number line. So it includes all the rational numbers and it includes all the irrational number also. Okay. So real number is a sum of rational numbers and irrational numbers, because rational numbers are also present on the number line and irrational numbers are also present on the number line. Because if you give me any example of irrational number, like under root of 3, this is a rational number because it is 1.732 something endlessly. But here it will, where it will be situated, it will be situated somewhere between 1 and 2 on the number line. Yes, because 1.7 is between 1 and 2, so it should be somewhere between 1 and 2, right? Can you hear me?
Yes, ma'am.
Okay. So what we say, that real is the sum of all the rational numbers, all the irrational numbers. So real number may be rational or irrational. So now every point on the number line is of the form of under root m, where m is a natural number. Yes. Every point on the number line is of the form of under root m. Is it true?
Yes.
Okay. It is saying every number on every point on the number line. Like if I draw 0, I have -1, -2, and -3. So if I can write down -3 as the form of square root, if I can write down like this.
No.
No. So this is false.
No.
Okay. So this is true for all the positive integers, but it does not hold good for the negative integers. So this statement is false. Clear? The reason is clear?
Yes.
Okay.
Yes.
Now question number 2. Are the square roots of all positive integers irrational? No. If I take a root of 4, if I take root of 16, these are rational. Okay.
Yes.
If I take root of 9,
yes.
This is 3. So this is rational. 2 is rational. 4 is rational. Under root of 1, this is rational. Okay. So we have done with this. So are square roots of all positive integers? No. All the positive integers, the square roots are not irrational. There may be rational also. Okay. So we can give a lot of examples, right? Like root of 1, root of 4, root of 9. Yes. So all these are the examples where the square root is a rational number. It is not a irrational number. Now, show how you can represent root 5. So we can do simply this way. Okay. You can take this, you can take a number line here, and then you can take this distance as 1, and this is also 1. So 1 plus 1 will give you root 2. Now, here draw a perpendicular, take this as 1. So root 2 plus 1, this hypotenuse will be root 3, according to the Pythagoras theorem. Now, if this is root 3, then again draw a perpendicular. So this will give you root 4. And if you take 1 again, you draw a perpendicular here, and now this hypotenuse will be root 5. Yes, because if you do the Pythagoras theorem, then this is square of root 4 will be 4 and square of 1 will be 1. So this will be under root 5. So this is the way you can continue. Clear?
Yes, ma'am.
Okay. Any doubt in exercise 1.1 and 1.2?
No, ma'am.
Okay. So now we come to the decimal expansions. Like we will continue with the irrational numbers. Irrational numbers, right? Okay.
Yes.
Because all these are irrational, either if they are like, if they continue endlessly, and if they are not repeating, and they are continuing endlessly, then we call them as irrational numbers. Let us go through certain examples. Like, find the decimal expansions of 10 over 3, 7 over 8, and 1 over 7. So you need to do nothing. Like, you simply find out, like the way we find the LCM, like it is 10 over 3. That means you need to divide the 10 with 3. Okay. So what you will have, because 3 3s are 9, so your remainder is 1. Okay. Then there is nothing left. So we put a decimal and we get a 0. Again, 3 3s are 9. So again, the remainder is 1. And since we have put the decimal, we can write down 0. So again, this is 3. So what do you think? Always the remainder will be 1 and we'll get a decimal and it will continue endlessly, right? It will continue
Yes.
endlessly. So the answer we will have always is 3.33333. It continues. Okay, it is endless.
Yes.
Similarly, it is like 7 over 8. That means you need to divide 7 with 8. Okay, now 7 is smaller than 8.
Yes.
So what do you need to put? You need to put a decimal. And if you put a
Yes.
decimal, then it will become 70. Okay, just for a moment, forget this decimal. Let it be there and just forget it. Now it is 70. So we need to divide 70. So 8 8s are 64. What is remainder?
Yes.
Remainder is 6. Okay.
Yes.
Now less than 8. But we have already put a decimal, so we can write down 1 0. Again, you need to divide the 8 with 60 with 8. So it is 8
Yes.
7s are 56. Now the remainder is 4. Remainder is 4. 4 is
Yes.
less than 8. So we write down 1 more 0. So now we have 40. Now 40 is divisible. 8 5s are 40. So the remainder
Yes.
is 0. So we will have 7 over 8 as 0.875. Okay. Now, if you can write down in
Yes.
the form of a rational number, 0.875. Yes. I will put this decimal out and I will write it as. Okay. Yes.
Yes.
Write down 0.875 like this. So now, is it a rational number? Is it in the form of a P or Q? Is it a ratio?
Yes.
Yes, it is a ratio. So this is a rational number. Because although we have the decimal, but we can remove the decimal, we can write down it in the form of ratio and the remainder becomes 0. So that means it does not continue endlessly, right? Similarly,
Yes.
we need to divide 1 with 7. So 1 is smaller than 7. So initially we put a decimal and we get it as 10. Now 7 ones are 7. 3 is the remainder. Then we put 1 more 0. So this is 30. Then 7 4s are 28. Remainder is 2. Again put a 0. 7 2s are 14. Okay. So as you can see, again the remainder is 1. So we come to this condition again. So what you will have? Again you will put a 0. Then 7 ones are 7. Then again remainder is 3. So we are continuing the same process again, right?
Yes.
Again, we will have 3, then we'll have 28, then the remainder is 0. So now we will go on repeating the process. So here we have 3 types of decimal expressions. In the first expression, it is continuing endlessly. In the second expression, it
Yes.
ends. It is completely divisible. It is a rational number. But in the third form, what we have? We have the repetitive. It is recurring. Recurring means the same thing is repeating again and again. Like if you have 0.142857, then again 142857, then again it will be repeated 142857. So although it is continuing endlessly, but it is repeating. Clear? The difference between these
Yes,
three is
ma'am.
clear. Again, it is
Yes.
it is not repeating. It is like it is repeating 3.33333. Okay. Here it is the 5 digits are repeating. Fine. So that is the difference. So first of all, you need to divide them and you need to find them, that if it is continuing endlessly, if this is repetitive or not. Right. So it is like if the
Yes.
remainder either becomes 0 after a certain stage or they start repeating themselves. Then in that case, what we can say that these are rational numbers. So case first is if the remainder becomes 0. Second is if the remainder never becomes 0. Okay, clear?
Yes, ma'am.
So these are just the example you can try. Like here you have 3.14. So this is not an endless. So we can put out the decimal and we can write it in the form of a ratio. So this is a rational number. Now, here it is repetitive, like 0.333333. So what is recurring? 3 is recurring. So we write it like this. Whatever is the recurring digit, we put a bar over it. Like if you have 0.33333. So what is continuing? 3 is continuing. So write down this as this. If it is like 0.134, then what is repeating? This
134.
134 is repeating. So you put a bar over 134. Okay. So you write it down in
Yes.
this. Clear? Any doubt?
Yes, ma'am.
Okay.
No, ma'am, no doubt.
Okay, no doubt. Now, how to calculate this? This is again important. How to calculate this? If you have this recurring sort of, then how to find down the digit? Because you have certain questions like this. So this is very simple. What to do? If like you are given with a decimal where 3 is recurring, this is like this. So we considered this as x. Okay, take this as x.
Yes.
Fine.
Yes.
Now, just see. How much is the recurring quantity? It is only 1 digit. This is only
Yes.
1 digit. So we multiply with 10 on both the sides. Had there been 2 digits that are recurring, so we will multiply it with 100. Got it? If it is like 0.34, it is recurring, then we will multiply both the sides with 100 because there are 2 digits. Okay? That is the simple logic. So this is only 1 digit, so we multiplied with 10 on both the sides. So if you multiply x with 10, so this will be 10x. If you multiplied this with 10, so what it will become? Just multiply 0.333 with 10. It will become 3.3333. Yes? Right? Right, so are you getting this thing?
Yes, ma'am.
Okay. So we multiply 10 with both the sides. So this is like this. So 10x is equal to now. Again, it is repeating. This is recurring.
Yes.
I can write it down as 3. Yes. I can write this
Yes.
down as this. Okay. So this will be tan x is equal to 3 plus. Yes. I can write this down as this. So this is 10x is equal to 3 plus x. So what you need to remember, first of all, just see the digit which is recurring. If it is only 1 digit, you multiply with 10. If there are 2 digits, you multiply it with 100. If there are 3 digits, you multiply with 1000. Okay. Now next step is that we need x on the right hand side. Left hand side, we are already having the x. So right hand side, we need to make 1x. So whatever is extra, write it in the form of addition. So here we have 3.3. So this is recurring. This is x. So we need to separate this. So we have written 3 plus x. So now it is 10x equals to 3 plus x. Now shift x this side. The 10 minus 1, that is 9x. So 9x is equal to 3 or x is equal to 3 over 9. So what we have done, we have just simply calculated this recurring quantity in the form of P over Q. So we have now can say that it is a rational number. 3 over 9 is a rational number? Yes?
Yes.
Cancel it out, 1 over 3. This is a rational number. Okay? So by using this technique, you can prove that if it is a recurring decimal number, then it is a rational number. So always imply this technique. Now here also they have shown it is 1.272727. So what is the recurring digit? It is 27.
27.
27. So 2 to 7 are 2 digits. So both sides you will multiply with 100. Not with 10, with 100. Okay. So 100.
Yes.
X as this recurring quantity. Then 10x is equal to this. Now we need x here. So how can you have the x here? You can write it down as, you have to make it, in order to make it as x, what do you need? 1.2727. because that is positive x. Okay.
Yes.
So just pay attention here. So how will you break this? This is like left hand side we have 100x and right hand side what we need? We need 1.2727 because we need an x and this is x. Okay. So if I remove x from this, what is left? 127 minus 1. So that is 126. Right? Now this is x. Okay. So just remove x from this. So 100x is equal to 126 plus x. Now you can calculate it easily. 100 minus 1 is 99. X is equal to 126. So x is equal to 126 over 99. Is it clear? That right hand
Yes,
side
ma'am,
we
it is
need
clear.
1x. Right hand side we need 1x. That is the only technique you need to follow. Just make 1x. Okay?
Yes. Yes, ma'am. Ma'am,
Yes.
for like how long are you going to like take like this class for today? Like how long?
I was supposed to take for 1 hour only, but let us see how much I can do. Fine? Okay?
Yes, just a second, ma'am. Okay, ma'am, can we continue?
Yes, we can continue. Do you have something else to do?
No,
want...
ma'am, we can continue with it. No problem.
Okay, okay. We will try to finish up as much as possible today, and then we'll continue tomorrow. Okay.
Yes.
So whatever we learned till now is if there is a decimal expansion, like we have done the decimal expansion by dividing. Now, if it is either terminating, okay, it terminates means we have the remainder as 0. That means it terminates. It does not continue further. Or if it is not
Yes.
terminating, but it is recurring, like if you have like 2.147, So there are two types. Either it is like 3.57 and then it terminates. Okay, terminates, the remainder
Yes.
becomes 0. Then it is a rational number. Okay. And the next
Yes.
thing is, if it is like it is not terminating, it is continuing. Here
Yes.
it terminates. Here the remainder becomes 0. But in the second case, even if the remainder doesn't become 0, but whatever we are getting, it is recurring. So it is like 2.147. It is recurring. So if it is recurring,
Yes.
then also we call it as a rational number. Like we have done just now. For the recurring quantities, we can write them in the form of decimal. Yes. Okay. So there are two conditions. Either if you are dividing, if you are having a decimal expansion, then either it terminates, it ends, the remainder becomes 0, then we call it as a rational number. And in the second case, it does not terminate, it is continuing, but it is repeating or it is recurring. Recurring simply means repeating. So we are having 147, 147 repetition. So again, it is a rational number. But in the case, if it is not terminating and it is not repeating also, okay, so what we call it as? We call it as non-terminating, non-recurring. That means neither it is terminating, neither the remainder is 0, it is continuing, and also it is not repeating. Okay, then we call it as a rational. Clear? So these are the three cases. Either it terminates, the remainder becomes 0, so rational. If it repeats, it continues endlessly, but it repeats, then also it is rational. But if it is continuing endlessly and also it is not repeating, then it is irrational. Clear?
Yes.
Okay. So you need to look for only two things, like either the remainder becomes 0 and it ends, the division ends. And if the division doesn't add, then we get the things as repetitive. These two cases only we will have the rational number. And if it is continuing, also not repeating, then we call it as irrational. Right?
Yes.
Any doubt? Any doubt? Like you can see under root of 2. This is like it is not ending and either it is not repeating. Can you see? It is not repeating and it is not. So this is irrational. Pi, the value of pi, it is 3.4141592. It is neither ending nor it is repeating. So what it is? It is irrational.
Yes.
It is irrational.
Yes.
Okay, here also they have explained that we take as an approximate. Whatever we take 22/7, it is just an approximation. This is not the exact value. So pi is an irrational number. Okay, what is pi? Pi, we take the approximate value, but in actual, it is a irrational number. Clear? Okay.
Yes.
Now, how to find the irrational number? There's a very simple technique given to you. Like if you need to find the irrational number between 1/7 and 2/7. So what you can do? We have just divided 1/7. It was like this. We have just done 7 and 1. Then we put a decimal. It is 10. Then 7 ones are 7. Then it becomes 3. We put a 0. 4s are 28. Yes? Okay?
Yes.
So that is recurring. Recurring because you will always get 142,857. So you can find out 1/7 by the method of division. So what you get? You get this as the answer. That this is a recurring. Now, you can also calculate 2/7. Now you need not calculate it this way. This is just the double of this because 1/7 is just the double of 1/7. Okay. So whatever is the quantity you are getting, just multiply it with 2. So you will have 2/7. Okay. Now we need to find the irrational number. So how we continue? So you can find any number between these two decimal numbers. Like this is 0.142 and this is 0.2857. So you can take any number between 0.14 and 0.28. It may be like 0.18 something. It may be 0.15 something. It may be like 0.20 something. All these values will lie between these two numbers. Clear?
Yes.
Okay. If you have any doubt, please ask.
Okay, ma'am.
Now, write the following in decimal form. That you can easily do. This will be 0.36. Now you can divide this 1/11. Yes. Like just we have done 1/7 we have just done. So similar ways you can do 1/11. Yes. So if it is like you can put a decimal, this will be 0. Again, you need a 0. So this way you can do. Right? This way you can do.
Yes.
Now this is 4/1/8. So first you need to make it to a proper. So this will be 33/8. Now you can simply divide it and you can get the value. Yes. It also 3/13, 2/11, 329/400. Okay. So you just need to find out that these are terminating or non-terminating or recurring. Fine. So you need to simply divide them. Nothing else. Simply divide them. Now the value of 1/7 is given to you. Can you predict what is the decimal expansion of 2/7 and 3/7, 4/7? Okay. So you need to simply divide or multiply. 2/7 will be 2 multiplied with 1/7. 3/7 will be 3 multiplied with this. Okay. 4/7 will be 4 multiplied with 1/7. 1/7 is already given to you. So just simply multiply this value with 2, multiply this value with 3, 4, 5, and 6. Clear? And you need to do it without the long division. No, we are not doing any division. We are just simply multiplying this value. Clear? So you need not divide it again. Right? Now, you need to express them in the form of P/Q. So how can you do? The similar way we have done. Like if it is recurring, 0.666666. Okay? So this is like 6 is recurring. So we take X as this value. Now, how many digit? There is only one digit. So we multiply both sides with 10.
10.
Okay. So this is 10x is equal to, now if it is multiplied with 10, we have 6.6666, right?
Yes.
Okay. So this is 10x is equal to, now this is 6 and 6 is recurring. Okay. Now, what I need x in left hand side I already have. So right hand side I need one more x. So how can I make one x? What is x? X is 0.6 recurring. Okay. So I separate this.
Yes.
So what is left? What is left? 6. 6 is left. If I remove 0.6 from 6, what is left? 6 is left. Okay.
Yes.
Now this is x. That is what we need. We always need 1x. Okay. So now x will go
Yes.
here. So this will be 9x is equal to 6, or x is equal to 6 over 9. That will give me 2 over 3. So what is the answer? This is 2 over
2 over 3.
2 over 3. Similar ways you can do. Here it is like 2 digits. So you will take it as x, and then you will multiply both the sides with 100 because there are 2 digits, right? Then on right hand side,
Yes.
you will make 1x. Then you will get the value. Now it is like this. How many digits are there? There are 3 digits. So I will take it as x, and I will multiply with 1000 both the sides. Is it clear why 1000?
Yes.
There are 3 digits which are recurring, right? So this is the simple
Yes.
technique you can do. Have you tried these questions? Have you done in your notebook?
Yes.
Okay, then you can revise them easily. Okay, and whenever
Yes.
you are having any doubt, just ask me. Okay, this also you can do. Are you surprised by your answer with your teacher? So what is the answer? Are you surprised by the answer?
Actually, yeah.
What is the answer?
It is, according to what I remember, it is 1 upon 9, something like that.
Okay. 1 over 9.
I think it's something
Okay,
like
so
that.
you just check it because it is like 0.9. So 9 is recurring, right? So we have 9 as recurring, so we can write down x as this. Now there's only 1 digit, so I multiply with 10 both the sides. So this is 10x is equal to 9.9 is recurring. Now I need 1x, so I will separate this 0.9. So I will have 9 only. So this is 10x is equal to 9 plus x. Okay. So 10x minus x, 9x is equal to 9. Or x is equal to 9 over 9. Okay. So that is the thing. So x is equal to 1. Right? X is equal to 1.
Yes.
That is why it is surprised. Okay. So why are you surprised? Because whatever is 0.99999999, so it is very much close to 1 because 0.9. Yes. If you have
Yes.
0.99, then we normally write it as approximately equal to 1. Yes. So that is why we are getting it like this. Okay. So if it is continuing endlessly, then there is not much difference between this value and 1. Okay.
Yes.
If you are like 99.9999% sure, then you say, no, I'm 100% sure. Yeah. So that is the same thing. If you have 0.9999, that simply means 1 because these values are so close that by calculating this value, we get that approximation. Clear?
Yes.
Clear? Now this is like 1 over 17. Then you can calculate this. Look at several irrational numbers in the form where p and q are integers with no common factors. Right? 3 numbers whose decimal exponents are non-terminating and non-recurring. That means irrational numbers. Yes? You need to write down the irrational numbers. So have you done this?
Yes, we have done this in notebook as well.
Okay. So you need to simply define the irrational numbers. Fine?
Yes.
So, okay, 3 numbers. We need to write down only 3 numbers. So you can take example of any irrational numbers. Can you give me an example of any? Yes, pi. Then root of 2 and root 3. Okay, and maybe root 5 or root 7. Any one of these you can take. Because these all are irrational numbers. So always we will have non-terminating and non-recurring. We need not search for. Because all the irrational numbers, they are always non-terminating, non-recurring. You can take root of 7, you can take root of 10, root of 11. All these, they will give you non-terminating, non-recurring. Clear?
Yes.
Clear? Okay.
Yes, ma'am.
Now you need to find out, find 3 different rational numbers between the, now you need to divide. Okay, divide this and divide this. So whatever is the value you are having, then you can find out the numbers between them. Fine. Now classify the following as rational or irrational. So for this, what you need to do? Either you can divide it or like the root of 23. Can you find root of 23? No. No. Because root of 23 is We cannot find the square root, so it is irrational. Under root of 225, that we know, because that is the, you can write it as under root of 15 into 15. Okay, so that is 15.
Yes.
So that means it is rational. Okay, now
Yes.
tell me for this 0.3796, it is rational or irrational?
This is rational.
This is rational because it terminates. It is ending here. Okay, it is not continuing. So I can write this down as like this. Fine. So
Yes.
this is the ratio. So this is rational. So whenever the decimal expansion is terminating, it is ending. It is always rational.
Yes.
Now here you can see. Here it is not ending. But is it recurring? Yes, it is recurring because we have 7.478, 478, 478. So it is recurring. And if it is recurring, that means it is rational.
Not
Rational. Okay. Either it terminates, or if it doesn't terminate, it is recurring. Okay. Two conditions for rational. It terminates. Like here you can see 0.3796. It ends here.
Yes.
So it terminates. And if it is not terminating, then it is recurring. These are the two conditions for rational numbers. Now here you can see it is recurring. Okay,
Yes.
so it is rational. Now here you can see for the fifth one. Okay, tell me for the fifth one. It is 1.10.
This is
Yes.
This is irrational.
Rational or irrational?
Irrational.
Irrational, right. Because it doesn't satisfy any of the conditions. First of all, it is not terminating because it is continuing. Second, it is not repeating. So it is not recurring. So not terminating, not recurring. So it is obviously irrational.